I will share the screen, and it is here. Let me know when you're ready to see the screen. Can you see the screen?
Yeah.
All right. So we'll start with chapter 5, SPM physics, electronics.
All right.
Right. So step 1, we have 9 steps. If you've forgotten the 9 steps, so they are all listed down here. And we'll start with step 1. And this is, what is the time now? 5:57 a.m. All right, let's see what time we stop. And step 1, we have 3 drawers. 3 drawers. The number 1 is electron. Number 2 is semiconductor diode. Number 3 is transistor. I created a very small, funny story. And let's see whether this makes sense to you, for us to remember these 3 drawers easily. So, have you been to a concert?
Yeah, kind of.
Okay, good. So concert, there are many people, and it's very crowded. And concert, you have policemen, and you have people who is checking your ticket to allow you to go into the ticket. And also there are policemen to ensure that the traffic flow is done properly in that outside the concert area. So electron is you, for example. Somebody is called electron. She is going to a concert, and she met with a policeman. And this policeman, the police traffic man, the traffic policeman, they usually tell you to go one way.
Yeah.
Okay, you cannot go to the other way. You cannot go to the opposite direction, because they will make the crowd flow very messy, and it will stop the flowing of the people. So this is the policeman that is telling you the one-way traffic. Then when you reach the concert, the main gate of the concert, they will have somebody who is checking your ticket, and that is the transistor. And why do I say that this is the man who check your ticket, and why transistor is checking your ticket? It's because transistor, once you see the ticket, then he will allow you to go into the concert. And when you go into the concert, you'll be extremely happy, right? This is a little bit of the function of transistor. Later you will know what is a transistor if you haven't know what is transistor yet. And also they will know a little, the policeman one-way traffic is showing a little bit of is telling you a little bit of the function of the semiconductor diode. Right, so we have transistor, we have diode, and we have somebody is called electron, who is trying to go into the concert. Yeah, before that, if on a scale of 1 to 10, 10 is the best, 1 is the weakest, where do you think you are in this chapter 5, electronics?
Maybe like a 5.
Maybe like 5?
Yeah.
Okay, so do you have some idea about what is electron, what is diode, and what is transistor?
Kind of, yeah.
All right. Can you tell me like very simple sentence, like 1, 2 sentence, what is electron, diode, and transistor?
All right. Hold on, let me think. How do I say? So electrons, there's like what terminal emission, if I remember correctly. There's like there's electrons are emitted from the cathode. I remember that. There's factors that have influenced terminal emission. I think there's like 5. I think there's 5 factors. There's like type, the platings. I think it was potential difference, the phase area, and there were characteristics for I think cathode rays. Yeah. They move in a straight line, and yeah. Semiconductor diode is what's it? There was like a doping process. There was different types of semiconductors. I think it was N type, P type, yeah. And and the diode works in different ways, I think. There's forward and reverse bias, I think, yeah. And for transistor, there was, let me see, everything. Transistor, there was two types, PNP and NPN. I think there was a formula. I think transistor is like mode something else. Yeah.
Yeah, that's the formula. So there's a E, B, and a C, emitter, base, and collector. I think on a high level, you know what is electron, what is semiconductor, diode, and also transistor. I think this chapter will be relatively easier for you to follow. And yes, I have to re-emphasize this again. I'm not a physics teacher. I'm teaching this brain drawer method using physics. For this case, will be physics chapter 5. So we are learning this together using brain drawer method and see how far or how efficient it will let you to understand this chapter better from 5 that you mentioned just now to maybe something higher to into 7, 8, or 9, or even 10. Right. So we have done, excuse me, we have done step 1, which is to create the drawer. There are 3 drawers, and that 3 drawer we already translated into a very simple story where electron is going to take part in this concert, it's a musical concert, and she met the traffic police, and she met the person who is checking the ticket. Right. So this is done. Let's go to step number 2. Step number 2 is to read the keynotes. So you can quickly read it drawer by drawer. And then once you are done, let me know. Then we will find out some keywords.
Alright. Measures the phrase free electrons from the atom. And cannot six. Alright. And use sorry. And five. Controlling system. Alright.
Okay.
Yeah.
So do you still remember the story, how to relate this with these 3 drawers?
Yeah.
Right. So we have electron going to a concert and met the traffic police, and also after that she has to meet the ticket check the person who checked the tickets before she is allowed to go into the concert and be super happy about meeting her idol over there inside the concert. Right. So let's start with electron. Electron is the first drawer. I'll just bring up the picture, the very ugly picture. Right. This is just a picture that is drawn by me. You can draw your own picture that is relevant to you, as long as the story is interesting enough for you to be able to understand it and to understand what is inside each drawer. So I have electron. Electron is the thermioid emission like you mentioned just now, and the cathode rays. Basically, it's talking about free electrons from the heated metal, and then it was being transmitted in a vacuum with a high, extreme high, HEHT, extreme high, we will know that term later, power supply, and cathode electrons to anodes and cathode rays. So what this picture is talking about, you can name this Dominica, or Dominica is some from my point of view, it sounds similar like thermionic, or you can name it for Veronica, or you can name it as Teresa, whichever name that makes more sense, that to help you to understand later this thermionic emission. And thermionic emission, this Dominica is negative, is a girl. And Arnold is positive, is a very strong man. And Dominica is always attracted to Arnold. So she fly over the vacuum to meet Arnold. Why is it a very strong man? Is related to this EHD, right? So that is how we put this story, very small story, into our first drawer, which is the electron that is going into a concert, right?
Yeah, okay.
So there is velocity. Velocity means, she is running very fast to meet Arnold. So now let's go to drawer number 2. Drawer number 2 is the traffic police that is only telling you one way, right? So what is inside here? What is inside the drawer? Inside the drawer, we have this car, creator car, where it's driven by Ali and Katie, who is inside the car. Ali is the positive, Katie is the negative, which means the boy and girl, and they are traveling to somewhere, to this concert, right? Let's say it's to this concert. So there are two ways. Ali and Katie can decide to turn left or turn right. On the left, which is this way, there are 4 humps, and there are 4 humps, so it's more bumpy. It's more bumpy. And for the right way, there is 2 humps, so there's less bumpy. So this is to explain the full wave and the half wave later, which you will know later. Right. I can't remember why I put this 4 capybara, but later we will know. Let's see. Yes, yes.
Capacitor, is it?
Yes, capacitor. You're right. Yes. Because I drew this about 1 month or 2 months ago, so I can't remember exactly why I put it. Yeah, so there are 4 capybara hiding under the humps. Right, so that is to explain the capacitor. Yes, good. Yes, good catch here. So let's go to transistor. Transistor, which is the third drawer. And this transistor is the person who stand at the gate to check your ticket. So transistor can also related to ticket, T. No, what is inside the story here? We have Bala, and we have Katie, and we have Emily. This is to represent the base, the collector, and the emitter. You can create this story as Bala has 2 girlfriends, and the first girlfriend is Katie, and the second girlfriend is Emily, right? Then the second story is talking about there is a big gathering, and this big gathering is talking the topic of the gathering. The reason for them to go to the gathering is they don't like pizza and noodle. So no pizza and noodle. No means N. PN. PN is to talk about to point on the PN, NPN. So NPN. All right. So there's a gathering, and when you are when they are in the gathering, they are obviously there is a loudspeaker amplifier, right? The amplifier is telling you that okay, no pizza and noodle, and then when the police come, they check Bala's IC because Bala, Kathy, and Emily was there also. So they check Bala's IC to make sure that he is not an illegal immigrant. Right. And in that gathering, when it's becoming night, turning darker, the sky is turning darker, then more people likes to come. And when it's colder, then also more people likes to come into the gathering. Right. This is going to tell you a bit more of the thermistor and also the LDR. Okay. Dark LDR, the darker it is, the higher resistance. cold the thermistor, the colder it is, the lower resistance. But don't worry about this, as I say in the previous few sessions. Just remember the keywords for now, then you understand it better. So now we have done step 2. So now we have done step
Yeah.
2. So let's do a recap. Drawer number 1, what do you have inside? And what is the
Okay,
name
now
of the drawer?
alright. The drawer number 1 is electron, and it's about the thermic emission. There's Teresa, which represents thermic emission, and she's running, which is the terminal velocity. She's electron, which is like negative, because she's a female, and she's attracted to Arnold, who is positive, aka like the yeah, proton. And for the second drawer, it's the semiconductor diode drawer. There's Ali and Kathy in the car. And there's 2 ways they can go, which is the one with the 4 bumps, which has like 4 capybaras hiding under it, which is like the capacitor. And then there's the other path, which is the full wave and the half wave, which, yeah, that's what those symbolize. As for transistor, there's Bala, Kathy, and Emily. Bala is the base, Kathy is the collector, and Emily is the emitter. There's this gathering, whereas this guy's like talking about like no pizza and noodles, which is the no PM. And they check Bala's IC, which is IC over iBala. And when it's dark, there's more people. When it's cold, there's also more people, which is for the LDR. And there's also the formula.
Right, the very, very famous formula. Right,
Yeah.
so now we have done step 2. Step 2, finish. Let's go to step 3. Step 3, I will put this here, keynotes on the left, step 3 on the right. Let me just do a very quick arrangement. And I will also pull out that techniques. You should know the technique by heart now, but it's okay. We will just pull it out just in case you need the reference to know what you need to do in each of the steps. Zoom in so that you can focus on the part that is relevant. I'll put it down here. This one I'll keep it aside. This one I'll keep it aside. Reduce clutter. Right. So let's scroll down to step 3. Pull up a bit, make it bigger. Right. So look at the red color part, the red color notes.
Yeah.
How do you read step 3? You read the notes, you identify which drawer, you tell yourself if this is a new information or new understanding. As the start, you will have more new information than new understanding, and then place it to the correct drawer that you have created just now.
All right.
Right. Okay, let's start with this one. Let's start now.
Okay. Emission of free electrons from heat.
EHT is extra high tension. Now we understand. Yes.
High tension. Ventilation and mechanics. Current affected by millimeters. Subscribe. Cathode to anode. Okay. Measure barriers inside the cathode uses required temperature factor. All right.
Yes. Like I mentioned to you just now, I studied this maybe 1 to 2 months ago. Also, I have to restudy this as we are following these steps. So, what is the new information that I can capture over here? Obviously, just now the EHT, I've forgotten what is it. Now I understood it. So this is a new information that I'll put it inside my first drawer. Right. Then what are the new informations? The electron beams. This is to tell you the cathode rays, cathode rays, right? So also, what are the new informations? I see that there is this coating. You apply different layers, and then the cathode can reduce the required temperature for emission, so it's more efficient, right? So if we relate this with the work function, you remember chapter 7, quantum physics, the work function.
Yeah.
The lower the work function, the more energy can be transferred to the kinetic energy of the electron. Right?
Yeah.
This is not exactly the same thing, but the concept is similar, right? So this is different coating, we have different work function,
Mm.
right? Okay. Yes, which drawer is this?
The first drawer.
Yes, obviously. Okay, let's try continue on the second part.
Multi-positives. And but okay. If I combine the two across resistance, not as spot here, and sometimes they have one. This is the all right.
Right. So quite a lot of new information over here.
Yeah.
Yes, which is the Maltese cross tube. I think you have done this experiment. I've done this experiment maybe 30 years ago, but I read this 1 month ago, so I try to remind myself what did we do that day. And there is this formula, EV equivalent to this formula.
Yeah.
Right. So these are the new informations. You can imagine that this who is this Teresa is driving an EV car, right? That will help you to remember the EV, right? And also you can remember for this, the Teresa is wearing a coat, wearing a very nice coat to make her pretty, but before she meet Arnold, right? So you can add those new information into your story or into your drawer, right? And the Maltese is like a cross. So maybe you can think of it like Teresa is also wearing a chain over her neck with a cross, right? So that will also help you to remember the important keywords for drawer number 1. Now, let's move to drawer number 2. Drawer number 2. Let's start reading this. Yes, and find out the information.
All right. And actually, all right.
Right, for this one, I have new understanding. The police, the traffic police is becoming clearer. Why the traffic police was there is because it is showing you either one way, either forward or either bias, or either reverse,
Yes.
right? And the difference between forward and reverse, the layer in between the P and N, either is becoming thinner or becoming thicker, right? So forward means the police car, the traffic police will always ask you to go forward, don't go reverse. So that is the flow. If you go reverse, then this is having higher resistance. People behind you will stop you from doing that. Even the police, the traffic police will stop you from doing that, right? So this is to explain a bit about the how this semiconductor diode works, right? And the rest, I think, is more about new information, also converting AC to
Yeah.
DC for this capybara of the bump and also the 2 bump and the 4 bumps, right? So let's
Alright.
go to drawer number
3.
3, the
Transistor.
transistor. Yeah.
MPE. Mm. Suppose. Alright.
The new information that I've got from here compared to the keynote notes are these 0.7 and 0.3. So this is to tell us that different materials will have different minimum voltage that is needed to be triggered, right? The transistor is like an amplifier, right? So this is mentioned over here. So there's not a new information, but it's more about more detailed this explanation about why it is an amplifier, right? If you do not know it now, later you know it in more detail with the other steps. But now at least you know that it is an amplifier. And you can also relate it with the story. When you are at the gate of the concert stadium, your excitement level is, let's say, at 3. But once you enter the gate and you see everyone is sitting in that stadium, your excitement level increased to maybe 7 or 8. But when you see your favorite singer who is starting to sing, then your excitement level went up to 10. So that is the amplifier, and that is the function of the transistor. Okay, let's continue this part before we go to step 4.
Okay.
Okay,
Almost, that's it.
yeah.
Alright.
Right. What I see here is more of a little bit of understanding. This is talking about the last sub drawer about drawer number 3 is on the thermistor and also LDR. So it's an application. How do you apply transistor into something that is more useful in our daily life? For the LDR is when the light, the sunlight or the light is dark, then it will automatically turn on the light. So you don't need to have somebody to go there and turn on the switch. So it's automatically based on the intensity of the light in that room. And for the heat, it's also similar. When there is a heat increase, the temperature increase, then it will trigger an alarm, for example, fire alarm. So you don't need somebody to run over there and turn on the switch. It will be done automatically. Or you can turn on a fan or turn on a aircon, depending on the temperature. Right. So that is step number 3. So let's go to step number 4. Before that, let's do the same exercise. We will review this. What is the techniques that is used that we need to use to follow to have this step number 4 completed. And this is training our skill number 3, storing new information. So you read the question, because this step number 4 is FAQ, frequent asked questions. Then you identify which drawer. Then you read the answer, and you see if there is new information or new understanding that you have, and place it into the right drawer of yours. By now, your drawer should be having more and more information or more and more story.
Yeah.
And there are eight questions. So let's start with this question number 1. Let's read the question first before reading the answer.
Thermite emission and cathode rays.
Which drawer is
This
this?
one is the first drawer.
Yes, the electron
Yeah.
drawer.
Yeah,
Okay.
the electron drawer.
Yeah, this one. Yep. So you can read the answer.
Yeah, release of free electrons. Observe heat. Okay.
Okay, any new information or new understanding that stand out?
That's an example.
Yeah, the tungsten example, right?
Yeah.
Yes, that's the new information. Okay.
Okay.
You can either think
the
of
second.
you can either think of some story or some items that you want to put it inside your first drawer. I think in the few session also, in the previous few session also, I mentioned that when we go into a deeper into the step 4, 5, 6, your drawer will be different from my drawer, and that is normal. Right. Then when you do your past year questions for the next 1, 2, 3 weeks, your drawer will definitely be different from any other's drawer. Okay. Now let's continue on question number 2.
Function semiconductor. This is the second drawer.
Yep.
One direction. All right.
All right. I think there's not much new information. Maybe if I want to take new understanding is the anode is always positive. The cathode is always negative. So when you terbalik, that means you do it the other way, then it is reverse. So it will stop the flow. Then yeah, this one you have to understand because this comes up quite a few times already. It is converting the AC into DC. Right? Smartphones that you have that you are holding next to you now, all the phones, they cannot have a AC being powered up, so they have to use DC. And the electricity that is coming out from your house, they are all AC. So that's how they are able to convert AC to DC to to charge your phone. Right. Let's go to number 3. This is drawer number 3, transistor.
Please open. Open. Okay.
Okay. Okay, let's go to the next one.
Also to draw Betty and Violet. I see, and Violet. Amplify systems.
Oops.
Ah,
Done?
yeah.
Okay, I think this one I need to show you the diagrams. This is the LDR, this is the thermistor. But before we go there, this is the diagram. They're showing the base, collector, and also emitter. So how do they do this amplifier? So when there is no this one, yeah, this one. So when actually there are two circuits. The two circuits is when this circuit is enabled, turn on, then these circuits will start to flow. So when this circuit is for this case, when it's depending on the light LDR, when the light is when it become darker, then it will turn on these circuits. So when it turn on these circuits, automatically these circuits will be turned on. So that is the function of the transistor.
All right.
Yeah, okay. Let's continue. That is to explain the IB and also the IC,
I see.
right? Yes, because I think just by reading, maybe it's not so easy to understand what is IC and what is IB.
I just remember I see it's like Katie the collector and B for Bala the base.
Yes, yes, that is a good start. Okay, let's go to number 5.
So it's also a transistor. It's not still the third drawer.
Yes.
Alternative light control switch. Oh, the light dependent. Oh, the dark. Oh, yeah, dark equals more people. Yeah. Society basis. Right. Oh, this basic remains off. Okay.
Okay. Yes. The strength of the brain drawer is to help you to understand the concept easier and faster. Right. But the weakness of the brain drawer is question like this. You need to do more exercise to practice. How do you calculate?
Yeah.
Yes. How do you calculate with that formula? With the formula. But at least this will give you some idea of the concept of there's IB and there's IC, and it is a amplifier. Right. Once you do more partial questions, then you understand the calculation question more. Then that will make you to be more exam ready. Okay.
Okay. Oh, heat control switch. So it's code equals to RP thing. So it's also a third drawer. Base resistor, base. That's also it's heat control switch. Alright.
All right. So this is talking about the thermistor.
Mm.
Okay, let's go to the question number 7.
Semiconductors. Oh, semiconductors. Yes, this is the second or second. Yeah.
This is drawer number 2 and number 3.
Semiconductors. Industrial Revolution, AI, 5G, algorithms. Oh, this is like a real life use. Okay. Okay. Alright.
Okay. This drawer number 1.
Yeah. Vacuum. Register electron. Image conditions. Yeah, the sun is there. External velocity, kinetic energy, critical electron beam. Value. Okay.
Okay. So let's take this opportunity to compare the keynotes and also the drawings. You read these keynotes again, and you find that you understand those keynotes better now. Yeah, let's read it quickly
Right, missions
in your mind. Yeah.
Okay. G-force. Mm. Alright.
All right. So when you see this picture, by now I think your drawer is different. Your Dominica or your Teresa is wearing a coat and is
And there's
running
a
very fast.
cross.
Yeah,
Yeah.
running very fast in a vacuum to meet Arnold. And then you have these semiconductor diodes where Kathy and Ali is driving. There are two ways. So there are 4 bumps and 2 bumps. And this 4 bump and 2 bumps is even clearer to you now. It's the AC to DC. And why AC to DC? It's because your phone is only able to accept AC. It can DC. You can accept AC. If you have accept DC, then the phone will burn. So you have to have another way to change it to DC. How do you change it to DC? That is the half cycle or the full cycle. And how do you do that? You're using semiconductor diodes, right? So now you understand semiconductor diode more and more, and how do you apply it? Then the transistor is even. You have the application on the thermistor and also the LDR. So it will automatically turn on and turn off based on the temperature or based on the light sensitivity, light intensity, right? Okay.
Okay.
So let's continue on the step number 5. And how do you read step number 5? Is similar, where you have to read the notes, then you identify which drawer, whether there's new understanding or information, you put it to your right drawer. So let's start from here.
Mm-hmm. Right, so it's here. XP was that. Okay.
Okay, I think there's no new information. Let's continue here.
What? Red lines. Cheese crust tube. And energy. Okay.
You still remember Fleming left-hand rules from our previous chapter?
Yeah. It was
Yes, the motto.
yeah.
Okay.
Which is the motion. This is the formula. Basis color display technologies. Okay.
Okay, let's move to drawer number 2.
Enter. Repeater. Enter. Open process. Okay. Sorry, guys. Data. Okay.
Okay, this part.
Okay.
Okay, there is a small new understanding here regarding the
Yeah, that's
capacitor.
moving.
Yes. So what does it says? It says that it is trying to smoothen it out. So now this is not smooth. Smooth means it is like a straight line. That is the best ideal case. Straight line, that means you are being charged your phone consistently. But if it is like this, that means you are not being charged consistently. You are being charged, then the charging is slower than the previous 1 second if it is coming over here. And then you go up again, then you go down again. Ideally, if it is a straight line, then that will be that will be the best. So how do we do that? We are using the capacitor. Capacitor is to discharge, so it will not go down to almost zero. It will be reduced, but not as good as like a straight line, but it's not as bad as a drop here. Then they will form it like almost like a straight line. So that is the function of the capacitor. Right. So let's go to draw number 3.
Yeah. And this is
Yes.
the
One thing is when I read this, I will tend to I'll tend to relate it to our
The
keynotes.
drawings and the yeah.
Yeah, the keynotes and then the drawer also. So I'm actually reading three things at the same time. That step number 5, step number 2, and also our picture.
And pin. Right.
Okay, last part here.
Switch. Switch. And okay.
Okay. Let me tell you something that I thought of just now. Okay, let me explain this one more time. This is like the automatic switch, and this automatic switch is a very small current. So this very small current, one is being triggered, then it will trigger another bigger current, right? So that's why when I describe it in the story, that before you go into the concert, your excitement level is very small. Once you step into your concert, you see all the crowd, you see your favorite person who is singing on the stage, your excitement level went up. So this is the amplification effect, right? So that is
That's
the role of a transistor.
all right.
And this explanation, they definitely will have calculations. And the calculation, like I said, you have to use another time to run that calculation by yourself, and that will make you familiar with those type of questions.
Hmm.
And the calculation is something using this,
Yeah.
using this
The
formula.
R squared over R1 plus R2 and then B.
Okay, now let's go to reading the quiz. It's still in step 5. How do you do that? You read the questions, and then you
Think of
tell
the
yourself which
answer.
drawer. Then at the same time, you form your own answer before reading the answer.
Yeah.
Right, this is to train this recall speed, trainable skill number 2. Let's do that.
Okay. Atomic emissions. This is the first row, and it's the emission of free electrons from the surface area. I'm pretty sure. 6 people. 6 people survives the tungsten filament. Sheet comes from. I'm pretty sure. Okay.
Okay, so you finished the answer already?
Yep.
Okay,
And
let's go to
no,
Answer not
Answer
yet?
not yet.
Okay.
Answer not yet.
Okay.
Oh yes, I am. Okay. Independent. Skip. Okay.
Okay. Let's go to number 2.
Okay. Race. Still the first row. Electron beams. Okay.
Okay. Answer number 2.
Um, Section, right? Oh yeah, that's yeah. Okay.
Okay. Number 3. The formula is wrong.
Oh, I think the formula was the EV is 1/2 mv squared mass, right? I think.
Yes.
Uh,
So you understand the formula by now.
okay.
Okay, the answer.
I thought another. Okay. No energy loss. All right.
Okay. Question number 4.
Semiconductor here. Okay. Second one, p-n junction is P is P type is the full, N type is the infection. Okay.
Okay. Number 5. Number 4. Answer.
The p-n junction, false electrons, is in condition. Okay.
All right. Number 5.
Rotate forward, reverse, and reverse bias. Oh, bias. Okay. Semiconductor, current flow, and depletion layer. Resistance. Okay.
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 Number 6.
AC cycles. Okay.
Okay.
So period on AC. Yes. All right.
Okay. Number 7.
Here's the rectification. This is still the second roller.
Yep.
DC. Smartphones can only take the DC or burn up. Or as AC to DC cycle using the semiconductor. Okay.
Okay, the answer.
Yeah. Mhm. Okay. Good.
All right, number 8 questions.
Transistor and resistor flow. These two influences. Para, Katie, Emily, base collector, emitter. Okay.
Okay, answer.
Yeah. Emitter, base collector, transfer, and transfer. Okay.
Okay,
NPN.
question 9. Almost there.
Base. Base to emitter. Was it? What was IC? IC over I bar. IB. Yeah. Okay. Okay.
Okay, answer.
Yeah, I see what I mean. All right.
Last question.
Oh, the LDR, which is the target, more people like control. Okay.
Okay,
Yeah, LDR's resistance is high. High voltage across more people, more resistance, higher voltage. And just have too much people, based on flow, especially to allow the blood to. All right.
all right. I suddenly thought of something interesting. All right, this one. Let's zoom in a bit. This is LDR. When it is dark, then it will turn on the light because this is
Yeah.
a light. What if I put this LDR and I swap it over here, and this R, I swap it over here? What happened?
The resistance would block it off, right?
Hmm?
No, like the resistance.
Yeah, I swap this thing and this one. I swap them.
I don't think. Hold on. Let's see. Goes from there. Swap
Okay, the simple
the
answer is
resistance.
itebalik loh. Now, now when it is bright,
Right.
then it
Oh,
will turn on the light.
oh yeah. Oh, that reminds me of
Okay.
something.
Okay. So when it is bright, it will turn on the light. So this is how it will work. But it doesn't make sense. Why do you want
Yeah.
a light to turn on when it's bright?
This reminds me of an
Yes. Same.
experiment my brother did.
Yes. Same go to thermistor. Thermistor, you see, when it is hot, then it will turn on. But if you swap it over here, then when the thermistor is cold, then it will turn on. Okay.
Okay, okay.
So you have to see
Makes
that you see
sense.
the LDR is 在下面的 okay below thermistor 是在上面的
All right.
so don't be confused if the question is asking you different giving you a
Like the
different diagrams.
different.
Yeah, giving you a different
Like,
diagrams for this because usually this type of question is to differentiate between A and A plus student. A student might know the concept very well. A plus student knows the tricky questions. So if you swap it over here, then what is going to happen?
then reverse. All right.
Right. Okay. So
I see. I
yep.
see. Makes sense.
Now, yes, just something I thought of just now when you were reading. Now, before we go to step number 6, we took almost 1 hour. So let's see, in this 1 hour, whether you understand this whether you feel that you understand this more. Let's
Okay.
read these keynotes again.
All right. And the database regulation is electrons repeat the metal surface. There is the tungsten 6 the tungsten H goes up to pieces. The risk with straight line, shadows, fluorescence, and it's the melted cross. And it was electron beams. Okay. Here. Semiconductor in one direction. Terrestrial the AC to DC cycle is in semiconductor rectification. Or I experience. Okay.
Okay.
Yeah.
So this keynotes now makes more sense compared to
Yeah.
1 hour ago, right? And why Brain Drawer is so effective is because it is giving you a framework. Do you know what's a framework?
Yeah.
Like
The
a high
outline
level,
kinda.
yes, a high level guideline,
Yeah.
right? So when our mind is able to have three different drawers, and you are able to focus on these three different drawers rather than just one big chapter, your mind will be able to focus better, and your mind will
Yeah.
be able to understand better, right? So with that simple story that we started 1 hour ago, electron going to the concert and met traffic police who is telling her to go forward only, do not go reverse. And then when she meet the ticket people who check the ticket, that is a transistor. When she go into the concert, and it amplifies her happiness,
Yeah.
right? And that is telling you there are three drawers, and each drawer is having their own items or stories. And when that story form, then your understanding forms better, and you're able to anchor whether this information is related to drawer number one, which is electron. And then in the electron, now you already have a lot of information. You have the free electron, you have the velocity, you have the vacuum, you
Yeah.
have the who is this
The
girl?
cathode rays.
Teresa,
Yeah,
yeah,
Teresa.
and you have
And
the
it's the jacket.
Arnold,
The
which is a very strong guy. Okay, then you have the cathode rays.
Yeah.
Then the second drawer, you have the semiconductor diode.
Semiconductor
And that diode, yes, and you have the capybara, you have the full wave and half wave. And
It's the
why this
one-way
full wave and
direction.
half wave needed? Yes, to convert between AC to DC. And
Rectification.
why
Yeah.
DC is needed? Because your
Your phone only
lovely
accepts DC.
smartphones can only be charged using DC, not AC. And a
DC.
lot of other applications, electronic application, is only using DC, it's not AC, right? And then I think you know why DC is needed. That was in the previous chapter, chapter 4,
Yeah.
the AC of the transformer,
Yeah,
right?
transformers for electromagnetism.
Yes, you need to step up, you need to step down. That is the function of transformer. And stepping up, so you have less resistance, then less heat, then you can transfer more energy from the power station down to your house,
House.
right? Right. So now we are able to relate them better. Now you are cross chapter now. You are not only focusing on chapter 5, you're also able to relate it with chapter 4 that we studied
Yeah.
before, right? And that makes physics more and more interesting, because now
Yeah,
you
they click
can
together.
relate. Yes, you can relate, you can link all these things together. Then the drawer number 3 is the transistor, the ticket collector, right? So, and the transistor, you have the Bala, you have the Katie, and you have the Emily. Let's open that picture here, right? And then you have this, they are going to this gathering that do not like pizza and
No pizza and
noodle.
noodle. Mm.
Yes, that is the NPN.
Yeah.
And the more darker or the weather becomes, the more people comes in. The colder, the more people comes in, right? So that is to reflect the thermistor and also the LDR.
Yeah.
And yeah, and yes, and that's it. So let's move to step number 6, which is the easier one. and you know the trick, you know the technique, right? We want to
Yeah.
kill the flying brain problem.
Flying brain.
Right? And also at the same time, we want to extract any new information or new and understanding into your drawer. Right? Are we ready?
Yep.
Okay, let's turn it on and play the video.
All right, let's talk about the
你听到吗？ Can you hear?
Yep.
Okay, let's start.
unseen engine that powers, well, pretty much everything in your life. It's a technology so fundamental, yet it all kicks off with one simple, tiny action: setting a single particle free. Ever stop to think about what a self-driving car, the AI you hear about everywhere, and the smartphone in your pocket all have in common? I mean, they seem like totally different worlds, right? But believe it or not, they all share the exact same DNA, the same common ancestor. And it all begins here, at a scale you can't even see. The entire digital age, everything is built on one surprisingly simple idea: figuring out how to control a single electron. So how in the world do you go from one tiny particle to, the engine of modern civilization? Okay, first things first. We need our raw material. And in the world of electronics, we're not mining for gold or oil. We are mining for electrons. Our first challenge is just to get a whole bunch of them together in a
Drawer 1, okay? Drawer 1.
controlled way, which means we have to convince them to leave their cozy homes inside a piece of metal. The way we do this is with a process called thermal ionic emission. And honestly, the best way to think about it is like boiling water. You heat up water, it gets enough energy, and molecules start jumping off as steam. Well, it turns out you can do basically the same thing with metal. Heat it up enough, and you can literally boil off electrons. So here's the playbook. First, we use a power supply to heat up a little tungsten filament until it's glowing hot. That creates a cloud of these free electrons. Then, and this is the clever part, we use a really powerful high-voltage supply to create a strong positive charge nearby. The electrons, being negative, are instantly attracted to it. We do all this inside a vacuum so the electrons don't bump into any pesky air molecules, and boom, they accelerate across that gap and form a perfect high-speed beam. And that high-speed beam has a very famous name: a cathode ray. This was a monumental first step. We now have a reliable fire hose of electrons that we can point and shoot. But a fire hose is no good if you can't control the flow, right? So, how do we tame it? Making the beam was one thing, but making it useful meant we needed to be the boss of it. We needed a way to control its flow. And that brings us to our second component, which is basically a microscopic traffic cop for electricity. Meet the semiconductor diode. Its job is simple but absolutely critical. It is, for all intents and purposes, a one-way street for electricity. Current can flow through it one way, no problem. But if it tries to turn around and go backwards, nope, road's closed. The magic is all in how you hook it up. Connect it one way, what engineers call forward bias, and a little insulating barrier inside shrinks way down, resistance plummets, and the current flows right on through. But if you flip it around, reverse biased, that barrier gets super wide, the resistance goes through the roof, and the current is stopped dead in its tracks. It's an elegant little gate. Okay, a one-way street for electricity. So what? Why does that matter so much? Well, the power coming out of the outlets in your wall is alternating current, or AC. It's constantly flowing back and forth. But nearly all of our electronics, our phones, our laptops, they need a nice, steady, one-way flow. That's direct current, or DC. The diode is the little hero that performs this conversion, a process called rectification. Now, you could just use one diode. It would block all the current trying to go the wrong way, but that's super wasteful. You're basically throwing away half your power. The much smarter solution is to use 4 diodes in a special setup called a bridge. Instead of just blocking the backward current, this bridge actually grabs it and flips it around, so all the power ends up going in the right direction. Way, way more efficient. So let's recap. We can create electrons, and we can force them to go in one direction. That's a huge deal. But this third component, this is the one that changed the world. This is what took us from simple electronics to computers. Say hello to the transistor. It's got 3 little legs: the base, the collector, and the emitter. And this tiny thing has 2 genuine superpowers. It can work as an amplifier, making a small current much bigger, or it can be an unbelievably fast automatic switch. Let's tackle amplification first. The best analogy is a water faucet, or maybe even a giant fire hydrant. A tiny little bit of current flowing into the base is like using your pinky finger to turn the valve. And that tiny little twist unleashes a massive torrent of water. It's the same idea here. That small base current controls a much, much larger flow of current through the main body of the transistor, from the collector to the emitter. A small signal controls a big one. And how much bigger are we talking? Well, in a pretty standard example, the amplification factor is 156. That means for every bit of signal you put in, you get 156 times more out the other end. That is some serious leverage, and it's the transistor's first superpower. And here's where it all clicks together. This amplification idea is also what lets the transistor be a switch. Think about it. If a tiny base current turns the large collector current on, what happens when you turn that tiny base current off? The large current goes off too. It's a switch with absolutely no moving parts. And because nothing is physically moving, you can flip it on and off millions or even billions of times every second. So what's an automatic switch good for? You see them in action every single day. Ever wonder how a streetlight just knows when it's dark enough to turn on? There isn't some complex AI brain in there. It's just a single transistor, patiently waiting for its signal. The circuit is so elegant. It pairs the transistor with a sensor called a light-dependent resistor, or LDR. As it gets dark, the LDR's resistance shoots way up. This change lets a tiny bit of current flow to the transistor's base. That tiny current is the signal. It flips the transistor's main switch on, and a large current flows to light up the lamp. Simple, automatic. And the beautiful part is, you can swap out that light sensor for almost anything. What if, instead of light, you wanted to detect heat, like in a fire alarm? Well, you just use a different sensor. Instead of an LDR, you use a thermistor, which changes resistance based on temperature. When it gets too hot, its resistance changes, sending that tiny signal to the transistor's base. The transistor flips its switch, and this time, it powers a loud alarm. It's the exact same logic, just a different trigger. So let's zoom all the way back out. We've seen how to make an electron beam, a one-way gate to direct it, and a microscopic automatic switch to control it. These three fundamental ideas are, quite literally, the Lego bricks we've used to build our entire modern world. And that is not hyperbole. As the source material says, these inventions directly led to the digital revolution. Every microchip, the brain inside every smart device, is really just millions, or now billions, of these tiny diodes and transistors all working together in perfect sync. You know, it's just an amazing story. From the simple act of freeing one electron to building a global network of artificial intelligence, it all came from mastering these fundamental components. It really leaves you with a huge question. If these tiny switches built the world we live in today, what kind of world will the next generation of switches build?
Okay, do you see any new information? I think there's quite a lot of new information and new understanding.
Yeah.
Right, let's keep that in your drawer. Now let's continue on the podcast.
Yeah.
Welcome to the deep dive. Okay, just look around you for a second. Your phone, maybe a smart speaker, those automatic lights outside. Ever wonder what's actually making them smart?
Uh-huh. What are the tiny little engines driving all that cool tech?
Exactly. So today we're diving deep into, well, the absolute fundamentals. Electrons, semiconductor diodes, and transistors.
And if you're, say, a year 11 physics student, this is for you. We're basically going to unpack the core ideas you're learning about, showing how they connect to, the real-world electronics you use every single day.
Right. Let's kick things off with the electron itself, specifically in cathode rays. So you've got a metal, maybe like tungsten in an old bulb filament.
Yep, good example.
It's full of these free electrons. They're not stuck to one atom. And if you heat that metal up,
You give those electrons energy, kinetic energy, enough for them to actually jump off the surface. We call that thermionic emission.
okay, emission, they're free. Now what?
So imagine doing this inside a vacuum tube. Very important. The vacuum, no air for the electrons to crash into.
Right. Keeps the path clear.
Exactly. Then you put a positive plate nearby, an anode. Those negatively charged electrons, they get pulled towards it hard. They accelerate really fast, forming this focused beam.
And that's the cathode ray, this beam of speeding electrons.
That's it, a high-velocity electron beam.
Okay, so what are its properties? What defines this beam?
Well, first, it's negatively charged. Obviously, it's electrons. It travels in straight lines. unless you interfere with it using fields.
Fields, like electric or magnetic.
Both. An electric field pushes it towards the positive side. A magnetic field also deflects it. You can figure out the direction using Fleming's left-hand rule. Remember that one?
Hey, yeah, the hand rule. Thumb for force, forefinger field, middle finger current. But current's opposite to electron flow here, right?
You got it. And
Yeah.
fundamentally, it's about energy conversion. The electrical potential energy, which we often measure in electron volts, EV, gets turned into maximum kinetic energy. That's the half mv squared max.
And this whole setup, the cathode ray tube. That's how old TVs work, the big chunky ones.
Precisely. They literally used this beam, steered by fields, to paint the picture on the screen line by line. Wild, eh?
Crazy. Okay, so we can generate and steer electrons, but how do we precisely control the flow of current, like directing traffic?
Ah, now you're talking diodes, semiconductor diodes.
Yeah.
They are the one-way streets for electric current.
One way only. How?
It comes down to something called a PN junction, which is where two types of semiconductor material meet. Think of it like a very strict bouncer.
Okay.
If you apply voltage the right way, we call that forward biased, the bouncer lets the current through easily. Low resistance,
Any other way?
reverse biased. Try to send current the wrong way and the bouncer slams the door shut. Very high resistance, basically no current flows.
Right, a one-way gate. That sounds incredibly useful. Where do we see that in action?
The biggest application is rectification. That's converting alternating current, AC, stuff from the wall socket that goes back and forth.
Into direct current DC, flowing steadily one way.
Exactly. Your phone charger has to do this. The phone battery needs DC, but the wall gives AC. Diodes make that conversion happen, either half-wave or full-wave rectification circuits.
So my phone charger is full of these tiny one-way gates.
Yep. And another super common example, LEDs, light-emitting diodes. Same basic principle, but they give off light when current flows the right way.
Okay, so electrons are the workers, diodes are the gates. What about transistors? They sound like the next level up.
They really are. Transistors are kind of the cornerstone of modern electronics. They usually have three connections: the emitter, the base, and the collector, E, B, and C.
And they let a small signal control a big one.
That's one key function, amplification. A tiny current going into the base, IB, can control a much larger current flowing from the collector to the emitter, IC. It's like using a tiny lever to move a huge weight.
Amplification, got it. But you also hear about them being switches, making devices smart.
Absolutely. Their second major role is acting as automatic switches. This is where things get really clever. Imagine using a light-dependent resistor, an LDR.
Its resistance changes with light, right?
Exactly. So in the dark, the LDR has high resistance. You can set up a circuit so this high resistance allows a small current to flow into the transistor space.
And that small base current.
Switches the transistor on, allowing the much larger collector current to flow and power something, like a streetlight.
Ah, so dark, high resistance base current light on.
You got it. And when it gets bright, the LDR's resistance drops way down, cutting off the base current, and poof, the transistor switches off, turning the light off.
Clever. And you can do similar things with heat.
Yep, using a thermistor. Its resistance changes with temperature. Gets hotter, resistance typically drops. So you can design a circuit where above a certain temperature, the resistance drops enough to trigger the base current.
Turning on an alarm or maybe a cooling fan?
Precisely. It's this switching and amplification controlled by tiny inputs that makes transistors the heart of, well, everything from basic sensors to AI and all the automation in the fourth industrial revolution.
Wow. So wrapping this up then, we've gone from free electrons being boiled off metal
To diodes acting as one-way streets for current.
to transistors being these incredibly versatile amplifiers and smart switches. It all builds up.
It really does. And it all started with understanding these fundamental bits of physics, mostly figured out back in the 20th century.
It makes you think, doesn't it? These principles are still driving innovation today. So here's something to ponder. Knowing how these components work, what amazing new smart devices do you think could be invented, maybe using even tinier, faster versions during your lifetime?
Yeah, the possibilities based on these building blocks are, well, pretty much endless.
Okay, we have done step 7. Now let's go to step 8. What is step 8? Step 8 is the story. I think you already saw the story.
Mhm.
And by now, you can even draw it out easily.
Yeah.
Right. So like I say before, you need to be able to draw your own story in less than 1 minute, and that is your chapter, and that is where you are bringing the entire knowledge of that chapter into the exam. Some of the people, they have already do it so much they don't even need to draw. It's all appearing in your
It's in your
brain,
head.
right? So, but both is fine. Both type is fine. So let's see. Let's do this
Quiz?
third one. The last, yeah, the quiz, the MCQ. Let me get the chapter. Let me see, where is it? Chapter 5. Chapter 5. Yeah, physics chapter 5. Okay, while it is loading, let's open chapter 5 and have a quick look on this chapter. Zoom it out first. So there are 3 drawers: electron, semiconductor diode, and transistor. And this is talking about the introductions. So the first drawer, we have the electrons, and it's talking about the experiment of the cathode, forming of the cathode rays. And there's a vacuum. And why they put this 6-watt power is
The
because,
tungsten
yeah, the tungsten 6-watt power is because they are creating
electrons
this
to leave.
electron, to release this
Yeah.
electron to go from here to here. And how this electron move from here to here? Because there is another EHT power supply to make this metal to be a positive and negative. So electron naturally is a negative element. The electron will move from negative to positive. So this explains the characteristic of electron. Electron is negative, and electron is being attracted to positive, and that's being created by this EHT power supply when it's connected to these 2 metals. And then they are moving in on a straight line, and that is being presented with that multi-cross. Right, so multi-cross. Do you see a shadow over here? If the electron is not moving on a straight line, then you will not see shadow, because those electron that is not able to pass this cross will be hit on the will be collide on the cross. So you do not see the light coming through the cross because the electron doesn't pass the cross. Right. So that is to explain the characteristic of electron. It's negative. It is moving on straight line. And also they mentioned about I think these two. I mentioned about the Fleming. So the Fleming also is a part of the explanation about the electrons. Then next is talking about the formula, the EV formula, which is to this part. Maybe you need to do a bit more practice question, to the calculation question, for you to familiarize with those type of questions. Brain draw do not give you this this exposure because it's only about 1 hour, right? Okay, and semiconductor diode. This is semiconductor. So you have anode and cathode. Then they're talking about the reverse bias and forward bias, and the thin depletion layer, and also the wide depletion layer. Then the function of the semiconductor, so that your smartphone can be charged using the rectification process, where you have half wave using 1 diode, or you have full wave using 4 diodes. Right, you have 2 types: positive cycle and negative half cycles. And this
It's the
this is the capybara. Yeah, this
Yeah.
is the capybara. Yeah, and the capybara is helping us to make this line as straight as possible. Right. So transistor, now goes to transistor. You have the Bala You have the Cathy and also the Emily. Right. Then you have the transistor circuits. You have the PNP and NPN circuits. Right. So this type of you will see why do you have two types of circuits, like something like this, and the other one is something like this. Okay. The main reason is, if I go up, this one is having a small power to power up. Okay, let's look at this. This is PNP. Let's look at NPN. To power up these circuits, and when this power up this circuit and it's flowing, so there's this circuit can flow, right? But usually we do not have two type of power because the phone is so small, so we will have as much less power as possible to be located in the circuits. So we only have one power, right? And that power will enable this small circuits based on the R1 and R2. This is taught in chapter 3, the electricity, right? To calculate the resistance, the voltage, and also the ampere, right? If you not sure about this, that means your chapter 3, you need to revise this chapter 3 again, right? So we will not go into detail on how to calculate this because this is chapter 5, right? But the concept here is you have one battery, and this battery with this setup of this series setting, you are able to control the voltage that is coming out from here. And this voltage is a very small voltage. And when this very small voltage is being triggered, then the big voltage will be able to flow because that is the function of the transistor, like a switch, right? So that is the application. These are applications. The LDR, the light, and also the thermistor as the heat. And then these are the experiment, and that's it. And that's it, right? Okay. So now ask me, let's try. Ask me 10 MCQ without answer. Okay, let's do the same drill. Read the question, tell me which drawer and also which answer. But before that, let's assume that you're in an exam hall, and in the exam hall you draw this picture.
Yeah.
So you can refer this picture as you answer the questions. Okay, let's do that.
All right. For the first one. Okay, the first one is
drawer?
B because it's the first drawer, and it's
Okay.
electrons are emitted from a heated metal surface. It's B.
Okay, number 2.
The second one is also still electron, which is the first drawer. The cathode ray tube. B. It allows electrons to accelerate. Without,
Okay.
yeah. Third one,
Okay.
cathode ray is still the first drawer. Hold on. Reflected. Third one is C by both electric and magnetic fields, I think. Yeah. Oh, this one's the formula. EV equals 1/2 mv squared. EV cut. This one is B. Oh, semiconductor here. Semiconductor here is the second row and it's the wall. So it is B. Full wave rectification. Number 6, rectification is also still the second row. And it's about the full wave, so it's 4 capybaras, so it is C. About rectification. 7 is capybara, so it's capacitor. 7 is C. Transistor circuit. Oh, this one is, yeah, this one is still No, this is the third round, yeah. This is the phase collector emitter. This one is B. A transistor can function as an amplifier and also as a switch. 9 is C. Ultimately, like control switch like LDR. LDR is high in darkness. Darkness equals more resistance. More people, more resistance, which is higher. So it's B.
Okay, tell me the score. My score. I think you have one wrong.
Oh.
I think so. Let's see. No, I am the
Huh.
one who has one wrong. Okay, excellent. Congratulations. Congratulations again. Let's copy this. I'll send it to you. Right, congratulations again. Let me stop the video. Let me stop the video first. How do I stop the video? Yeah, stop the recording.